So while you guys are finishing that up, I'm just going to talk for a minute.
Yes. Is this kind of in general?
Yeah.
Doing that.
Me too. She said last time her dad ate my
I'm not sure what's going on, Sam. Why is it not doing anything for you?
Should I try like maybe like leaving the class and joining you guys? Sorry for taking a second.
No, it's okay. It's not that big of a deal. I don't know why it's not.
Because she goes, I saw it. I saw it. What did you see? Wait, what did you see?
Did you make this team, or did you? Was it?
Yeah.
This was here, right?
I think it was just there. I don't think I joined it.
She just, that wasn't anything bad.
No, the action said otherwise.
No, it wasn't. She did a whole bunch of them. It was the same thing that she showed you, all of us, like without a shirt.
Oh. Why did you say that? Yeah, why did it?
I saw it.
It? What is it? She was like, she looked at it, she goes, oh, it kept showing that.
I accidentally clicked, like, after I tried to scroll.
Right.
It's in my ear, so I'm just kidding. But, and then I was like scrolling really quickly, I was like, oh.
I saw it.
I already saw it.
The couple next to us.
It was not the one.
No,
You guys
it
are
was
being
like
insane.
the waitresses. Like, it
Well,
was the-
then they know that I saw it. Like, I don't care.
Show a health.
Dude.
Try this
I
one
felt
more
the girl
time.
behind us, like, looking at me, so
No, it's
like,
okay.
she was still on the ground. I could feel her, like, breathing on me.
I'll tell you guys that when I went to church on Sunday, Blake, James, and Abby, and they all were very friends. And like I didn't notice because I was trying to mind my own business, and all of a sudden she started really fucking talking. And I'm like, oh my, there's no way. I slowly turn around and I see them.
Okay. There it goes. Okay. I don't know what was going on, but I just closed out of Teams and restarted it, and everything seems to be where it's supposed to be now. So
Thanks, sir.
you should
I
be
just
good.
Open it in Windows or open it in.
Yeah. So you just do the little drop down like we did, and you should be good.
Okay, perfect. Thank you.
Yeah. No problem. Glad we could figure it out.
Yeah, just ask me when people come to my house.
All right.
Did that happen?
So should be good now, right? Everybody had a chance to do that. I'm gonna talk for a minute before we dive into new stuffs. So do a little short-term, long-term stuff going on. So we're gonna be starting this semester with the process of recovering a function from its derivative. So in first semester, we learned how to go from function to derivative. Second semester, the main focus is going to be taking derivative and recovering back the original function. And we'll look at like, okay, how do we do that process? What can I do with that process? Then like what kind of application stuff can I do? And that's basically the semester. Okay. There were 2 topics from first semester based on our final exams that I wasn't happy with the progress that we made, that we're going to, in this first month, kind of take a second pass through. Any guesses as to what I think those 2 topics going to be? Related rates and optimization. You got it. So the way that this will work is I'm going to give you guys like a set of related rates problems. I think I have 4 sets to give you guys. We're just going to kind of give them to one set at a time. So there's like 4-ish problems in a set. So I'd like you to do these for next class, and we'll take some time in class kind of going through these while we're doing the new topics as well. I think that probably at this stage of the game, you guys just need to practice stuff and get some feedback more than like hearing me explain how to do stuff more until you tried some stuff. And seeing me do examples, what you need is to try it first and then get some feedback on it. So we're gonna do that. At the end of these 4 sets of problems, we'll have like a mini test on the one topic. It won't be like a 100-point test, it'll be like a 25-point test or something. So it'll be like a small test grade based on just related rate problems. It'll be something similar where I'll give you like 3 or 4 problems to do, and we'll just grade that, and it'll be something little. It'll be a test grade, but it won't be a 100-point test grade. It'll be some smaller version, 10, 20, 25, something like that. And then we'll do the same thing for optimization. Everybody's okay? So we'll kind of have that running alongside this new content. Does that feel okay? Reasonable? This first set of related rates problems I gave you today is the this is the easiest set of like related rates problems. So they're going to get progressively more complex as we go, but today should be pretty reasonable. Again, we'll go through things next class, take questions and do some examples and all that jazz, but this should be pretty doable. Okay. For second semester, we're still going to do homework quizzes. There's still going to basically be 1 after every lesson. Okay. The homework quizzes now, though, instead of mostly being on paper, are going to be mostly through the MyAP. So they're going to be like, like some small set, like 4, 5, 6, 7 multiple choice questions that I'm going to pull from the MyAP. Those multiple choice questions will include the topic we most recently worked on and things from first semester. So like 80% new, 20% old. It's a cumulative course, it's a cumulative AP exam at the end. I don't want to ever get kind of too far away from those ideas we saw in the first semester. So we are still going to be, those things will still be cycling back through in the homework quizzes. Does that feel okay? Now these are multiple choice questions. They're graded on the MyAP, so they're like right and wrong. So we'll still have like, homework quiz would be like 10, 9, 7, 8, etc. But like, all right or one wrong will be like a 10, right? And like, maybe 2 or 3 wrong is like a not, like it'll go in kind of banded like that where you don't have to get 100% to get 100%. And like, you get them all wrong, you get like a 7 kind of thing. Is everybody okay? And we're gonna time it. So we're gonna put a time limit on these MyAP homework quizzes, just to get you used to working at a pace that you kind of need to maintain during the AP exam, because it's a time test that we're preparing for. Now we'll start out generous, and as the semester goes on, I'll be whittling some time off of these, especially depending on the topic. If it's something that, this is something you should be able to do fast, like I'm gonna take time away. This is something that like, okay, this is just like, some of these are just time sucks, like this is a whole black hole problem. It's gonna take, like there's no quick way through this. You might get a little bit of extra time on something like that. Or a black hole topic, where it has some like, whoop, I just stepped in it, now I'm gonna be here for 3-4 minutes, even if I know what I'm doing. So just kind of give you an idea of kind of what's gonna be coming down the pike. Does that feel okay? Because that AP exam is gonna be here before you know it, right? So this is part of we're gonna keep reviewing the things we've done in first semester, all semester long inside of these homework quizzes. So still hopefully keeping those things not so far away. And there are a couple of topics from first semester here that we're gonna start kind of continuing to practice on and try to get a little bit better at. Okay? Feel good? Today, we're gonna do section 4.9. Now, ideally, this would have been the last topic we would have done in semester 1. We didn't get to it in semester 1, that's fine. This is a great bridge topic between the things we're doing in semester 2 and the things that happened in semester 1. So it's an ideal place to either end or start. So no big deal. Matthew?
Are we gonna have a mini quiz next class?
Yeah. Yeah.
Sweet.
I know. What we're doing is not bad. Okay. All right. So again, the whole focus of second semester is going to be this process of starting with a derivative and recovering from it the original function. Okay? That process we can call anti-differentiation. So if I have some function and I recover from it the original, that original is called the antiderivative. So if I start with the derivative and recover the original function, we call that original function the antiderivative. And that process is anti-differentiation. Is everybody okay with the vocab there? So that's the first definition we start with. So our definition reads, a function f is called an antiderivative of, a function capital F is called an antiderivative of lowercase f on an interval I if f prime of x is equal to f of x for all x in I. So if I take the derivative of the antiderivative, I should get the function that I anti-differentiated. So for example, let's say we have the function 3x squared, and I want to recover from that the original. So like 3x squared is like my derivative. What is the antiderivative of that? What would have been the original function? Yeah, it could be x to the third. Now, we'll talk about how we did that in more detail here in a moment. If you don't see it right now, looking at it, it's okay. But if you look at x cubed and you take the derivative of it, the exponent of 3 becomes the coefficient, and you subtract 1 from the exponent, that's going to be 3x squared, right? Everybody's okay there? Is that the only antiderivative of 3x squared? Can anybody see another one? It's okay, second hour couldn't see it either. Let me write one for you. What about x cubed plus 1? What's the derivative of x cubed plus 1? Still 3x squared, right? Is that also then an antiderivative? Can somebody give me another antiderivative? Yes.
X cubed plus 1 plus 1.
Okay, so, or x cubed plus 2,
Essentially.
right? Everybody feel good there? Are there more? How many more? Infinitely many, right? So what we'll often do is we'll talk about the antiderivative as just x cubed plus c, where c is some constant. We refer to this as the general antiderivative, because we acknowledge there's infinitely many antiderivatives, but they all just differ by some constant. We'll just be arbitrary and say, okay, in general, it's going to look like this plus whatever that number is at the end. Could be anything. Is everybody okay there? Now, an important distinction here. In first semester, we thought about a mapping from a function to its derivative, where the function, or where the operator is the derivative, right? So input is a function, I do the derivative of it, output is a single function again, right? If I think about the anti-differentiation as the same kind of thing, input is some derivative. I do my anti-differentiation as my function, or as my operation. The output is the antiderivative. How many outputs do I have from that anti-differentiation operator? Infinitely many, right? So I have one input, infinitely many outputs. Is that good or bad? It's kind of bad, right? In mathematics, what's happening here? This anti-differentiation operator is not a function, because one input has more than one output. We don't love that. Is everybody okay? The differentiation operator is a function, right? If I take the derivative, I only get one answer ever, right? Function, that's good. Anti-differentiation, infinitely many answers, kind of bad. Okay? So we have to be a little bit more careful here. Now, surprisingly, in practice, anti-differentiation is typically easier than differentiation. In principle, it is way harder. Okay? So for the most part, the problems that we'll ask you to do to find the antiderivative of will be easier than the hardest problems we ask you to do the derivative of. Like I can ask you to find the derivative of like a 10-layer composition, and you can do it. We've done enough for you to do that. Now it stinks, it's gonna be hard, it's gonna be time consuming, but you can do it. The same is not true for these anti-differentiation problems. You have to be very careful about what I'm asking you to do, because there are things that there is no like formula to recover back the antiderivative from it. In fact, there's many integrals where there's no, or many anti-differentiation problems where there's no way at all, and the best you can do is like make an approximation. but that's like beyond the scope of this class. Just giving you an idea here of the big overall. Okay. So we talked about the antiderivative. That's this piece here. For the general antiderivative, that's that next box. I don't think we need to say more about that. It just means you have a plus c at the end. What I want to do is take a minute and talk about the how of finding these antiderivatives. Okay? Because you know what? You already have the rules that you're going to need. So let's show you through a couple of examples. So if I have the function f of x equals sine x, and I want the most general antiderivative, I need to ask myself, okay, I need to think back to my derivative rules. Do I have any derivative that gives me a sine as the answer? The derivative of cosine is negative sine, right? So if I just divide both sides by a negative, I can say the derivative of negative cosine is positive sine, right? Is that what I need? Yeah. So my antiderivative, the function whose derivative is sine, is negative cosine. And because I want the general antiderivative, that just means I tack a plus c on at the end. Is everybody okay with that and kind of how we thought about getting there? What was the key thing that I needed? My derivative formulas from first semester, right? Specifically, the derivative of cosine is negative sine. Let's look at the next one. So here my function is 1 over x. So I need to think back to my derivative rules. The derivative of what gives me 1 over x? Natural log. So I could say then that my antiderivative would be the natural log of x plus c. Now, I have to be a little bit careful here. What do I have to be careful about? It's subtle. It really puts the b in it. What's the domain for the natural log? It's not all real numbers. Has to be greater than 0, right? What's the domain for 1 over x? Well, not equal to 0, right? Negatives are okay for 1 over x. Do you see the problem? So what am I going to have to do here? Just going to make it the absolute value of x. That way, no matter what x was in 1 over x, it's still going to be in the domain of the natural log, right? So if x was negative 2, that's fine. 1 over x is 1 over a half. The natural log of negative 2, that's fine. That's a number that we can get. Okay. That doesn't happen very often. I think that's the only antiderivative that we have to be careful with the absolute value on, that we're going to deal with in this class, I should say. All right, last one here. F of x is equal to is equal to x to the n, where n is not equal to -1. Why do we have the not equal to -1? Because that's this case right here, right? X to the -1 is just 1 over x. We already did it. What do I need to take the derivative of to get an x to the n? What type of function is x to the n? It's like a polynomial, right? Specifically, it's a monomial. Okay, like x squared or x cubed or x to the 4th. What was the rule that I used to take the derivative of those? I subtract 1 from the exponent and I multiply the old exponent to the front, right? So what is the exponent that I'm going to have if after I differentiate I get x to the n? Well, n plus 1, right? Because we would have had to subtract 1 from the exponent when we take the derivative. Everybody's okay there? And then what else happens? I'd be multiplying by n plus 1, right? If I took the derivative of x to the n plus 1, I get n plus 1 times x to the n. Everybody agree? That's almost what I want, right? Because I want the x to the n. What's in the way? I have that times n plus 1 out front, right? Now that n plus 1 is just a constant. So if I just divide it by both sides, that'll drop off. And that's what I need. So if you think back, when I took the derivative of a polynomial, I multiplied and subtracted, right? When I'm doing the antiderivative of a polynomial, I am adding and dividing. You guys see it? How it's still kind of like the reverse process. So we have anti-differentiation here, right? What are the rules for anti-differentiation? They're just the reverse direction for the derivative rules you've already learned. Isn't that lovely? Remember when I was harping on you about how these derivative rules weren't going to go away, even when we stopped doing derivatives, that we still need them? This is why, because it's still the same rules. So here we've gone and consolidated our derivative rules into antiderivative rules. So we've just taken the function and its antiderivative. I've just kind of consolidated the rules there into a table. It's not all of the rules. We didn't do any hyperbolic geometry in this class, so don't worry about the Cauchys and Siniches. The H is for hyperbolic. Don't worry about it. You might do hyperbolic geometry in your college calculus course, but we don't do it for AP, or I don't think we do it for BC either. So you don't need to worry about it. It's somebody else's problem or a later problem, but it's not a now problem. Is everybody okay? Good news is, oh no, I just got a bunch of antiderivative formulas to memorize. Good news is, they're just the derivative formulas that I've already memorized in reverse. No, it's okay. Good news, bad news. All right, let's do another example. So here our derivative is 4 sine x plus 2x to the fifth minus square root x all over x. So remember how when we take the derivative of something, we can take the derivative term by term by term, right? You guys remember that? If you have like two things added together, you can just take the derivative of the first thing and the derivative of the second thing separately. You can consider them separately. We can do the same thing for anti-differentiation. Okay? And if I look at that first term, I have a 4 times sine x. When I have if I want to take the derivative of 4 times something, what do I do with that constant? Just kind of ignore it and keep it hanging around for the ride, right? Guess what? When I'm doing the antiderivative, I can do the same thing. Everybody's okay? So for this one, I can start by just taking the antiderivative of sine x. What's that? Negative cosine x. How'd you get that so fast, Adriana? Yeah, we just did it a second ago, guys. Like, come on, man. We just did it, right? Okay. So that part should have been relatively easy. Everybody, any questions on what we did to get that? It's okay? I'm looking at the second part, and it looks pretty scary, Mr. Kulak. What the heck do I do with this? What's that? Separated is an excellent answer, Anthony. What do you mean by separated? Yeah. Excellent, excellent, excellent. So Anthony says, let's separate it. And I'm able to do that because the denominator is a monomial, right? I could still do that if the denominator is a polynomial, but each denominator would have to be the polynomial, and it gets pretty messy. What do you notice about each of those two terms now? Yeah, we can reduce them, right? So I get 2x to the fourth minus x to the negative 1/2. Does everybody feel good about where I got those values from? Look at it for a second. Don't say yes till you see it. All right. We're good? Okay. What is the advantage of writing that second term like that? Right? We took this guy and we wrote it this way. Why is that helpful to us? Because they're both now in the form x to the n, correct? So I can just use that antiderivative rule. So I'm going to have 2, I'll write it this way. I'm going to have 2x to the n plus 1 over n plus 1. And then I have minus x to the n plus 1 over n plus 1. And now I'll just do a little bit of cleanup. And we'd be almost done. What did I forget to do? Yes, add plus c. Because it asks for all functions. That means we need the general antiderivative, so it does need a plus c at the end. one of the most common mistakes that calculus students make on their written or their handwritten portions of their test. And they're just like, oh my God, I can't believe I did it. I forgot all my plus C's. I did all the hard part. I forgot all the easy part. Matthew, what's up?
How did you get the 2 in front of the x and 1/2?
The denominator is a positive 1/2. So when I divide the fraction, it turns into multiplication. Right? I multiply by the reciprocal. Is that cool? Again, I wrote it without doing some of the nitty gritty, but if you don't see it, feel free to ask. I'd be happy to elaborate. That's the right thing to do. If you're wondering about it, somebody else is wondering about it too, so make sure you ask. Yes, Anthony.
You don't have to simplify it all the way, right?
That would be appropriate to leave at, yeah. Yeah. Again, to be honest with you, on a handwritten part, the previous step would still be okay, but there's no way the multiple choice answer is going to look like that. I would suspect the multiple choice answer would look like this, or possibly have 2 square root x at the end instead of to the 1/2 power. But I wouldn't expect common denominators and all that nonsense. That's more work than it's worth. I don't think anybody would reasonably want to do that. Does that feel good? Okay. Next question says, find f if f prime of x equals yada, 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 and f of 0 equals -2. What is this for? What am I supposed to do with that? Go back and read the directions for the problem again. Does it say find all f? Or to find the general antiderivative? No, that means it's asking for one specific antiderivative. How am I going to find the specific c? I'm going to use that stuff to find the c at the end, to figure out what is the actual number that I need for this specific antiderivative. Everybody's okay? We'll show you how to do that in a second, but that's the end. It's going to be the same process as before. We'll find our general antiderivative, and then as our final step, we'll use that point that it gives me in the problem to find the specific c that I need. Everybody ready to go? Okay. What's the antiderivative of e to the x? E to the x. I'm disappointed that only one person shouted out that answer. That was the easiest one of the whole day. I would have expected 16 responses, because I don't think anybody forgot the easiest derivative rule that we did, that the derivative of e to the x is e to the x. Yeah. All right. And then, okay, I see a constant, so I'm just going to kind of suck that out front. And I'll write my plus c here. What is the antiderivative of 1 plus x squared to the -1? Oh, guys. Yeah, let's think about it this way. And now you should recognize it, because I think Anthony mumbled it out. You said tan -1, or we'd want to say tan inverse is the way we'd say that. But yes, that is the antiderivative rule you're looking for. Again, remember, we had to have these things memorized, not just once, but forever. They're going to come up over and over and over again. So if you're still kind of shaky on these derivative shortcuts, make some flashcards, or find that Quizlet from first semester. Spend a little bit of time here in the next week or two just buzzing through these things till you stone cold know them. You'll be well rewarded for doing so because they are not going away, okay? All right, so we have this, right? That's our general antiderivative. So now what we can say is then if I plug 0 in for x, I should get -2. Everybody feel okay there? See what I did? What's e to the 0? 1. What's tan inverse of 0? Oh, guys. Okay. What's the graph of tangent look like? So this is the point here, 0, 0. So in tangent to 0, what is x? 0. So tan inverse of 0 is 0. So what's c going to be? -3? Oh, -1. Oh, no. So f of x would be e to the x plus 20 tan inverse x minus 3. Does that feel okay? How's this process feeling? Is this not too bad? It's going to stay like not too bad for a little while. What have you noticed that we haven't had to run in reverse yet? Any product, quotient, or chain rule, right? So as an AP AB student, you'll need to learn how to do the chain rule in reverse, but not product or quotients. If you're a BC student, or a student in my classroom also, we're going to do some product rules in reverse. And nowhere are you going to do a chain rule in reverse, or a quotient rule in reverse. We'll look at some other techniques to deal with the quotient of two functions that don't involve trying to run the quotient rule in reverse. That's a whole separate topic. There's a bunch of different techniques that we can use to get around that. And we'll look at some of those even in this course. Everybody okay? All right, let's look at the next example. So find f if f double prime of x is equal to yada, 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 when f of 0 is something and f of 1 is something else. What do you notice here when you read this? Yeah, we're starting at a second derivative and we have to recover the original function. And because of that, what do you notice that I'm getting? Instead of 1 point, I'm given 2 points. Why am I going to need 2 points? I'm going to get a c when I do the first antiderivative, and then a second c when I do the antiderivative of the antiderivative. So I'm going to have 2 c's to solve for in my final answer. Or 2 different c's, I should say. Is everybody okay? All right. So we'll start by just peeling back the first antiderivative. How do I do the antiderivative of 12x squared? Excellent. So again, all I'm using is this formula right here. So I'm adding 1 to the exponent and dividing by the new exponent. How do I do the antiderivative of 6x? What's the exponent on x? 1. So it's going to be 6 to the 1 plus 1 over 1 plus 1. And what's the antiderivative of 4? So, yes. So really 4 is 4 times x to the 0. So it'd be like 4x to the 0 plus 1 over 0 plus 1, or just 4x. Everybody's okay there? Now in this problem, I'm going to run into having two constants. So I'm going to use two different names for my constants. I like to use subscripts, so I'm going to call my two different constants C1 and C2. You could do C and D or M and N or whatever letters you feel like doing. I like subscripts, so I'm going to do that. Is everybody all right? Okay. Now, can I use either of the 2 points given right now to solve for this C? Yes or no? No, I cannot. Because the function that I have written down here is for f prime, and the points that I'm given are both points on f. Do you see it? So I cannot use these points yet. I'm going to have to do my next layer of anti-differentiation before I can use those points. Does everybody see it? Okay. Let's simplify this down, though, before we go, right? So that's going to be 4x cubed plus 3x squared minus 4x plus C1. All right, so antiderivative of 4x cubed is going to be 4x to the 3 plus 1 over 3 plus 1. Everybody see it? How about 3x squared? And then 4x. And then the antiderivative of C1, just C1x, plus my constant. Pause here. Have I lost anybody with what I've done? Does this feel okay? I'm still just using that same antiderivative rule over and over and over again, right? You think this is an important one? Yeah. It's a good one. All right. So what do we got? Let's simplify this down. So we have one equation with two unknowns in it, right? We're missing a C1 and a C2. Can I solve one equation with two unknowns in it? No. What do we usually have to happen if we have an equation with more than one variable and we want to try to solve it? You got to create a system of two equations, right? That's why you're given 2 points to create two separate equations, two variables in it. Now, in this specific instance, it's not that difficult. You don't actually need a system to solve this because of the specific points you're given. Which point in particular makes it unnecessary to create a system of two equations? Excellent, yes. F of 0 is equal to 4 because what that's saying is if I plug 0 in for x, it's equal to 4. When I plug 0 in for x, the only thing left is going to be C2, right? So what do I know? that C2 is 4 right away. Is everybody okay there? So if I use my second point then and plug the 1s in, I can then solve for C1 pretty easily. What do I get there? One plus 1 minus 2 plus 4. That's 4. Subtract 4 from both sides. I get C1 is -3. So my answer then is f of x equals x to the 4th plus x cubed minus 2x squared plus 4x, minus 3x plus 4. Is everybody okay with what I did there? Again, that's kind of the most difficult version of this kind of problem. It's all right? At least for now. So here we're given the graph of some function f, and we want to make a sketch of its antiderivative, given that f of 0 is 2. So I'm going to start by just plotting that, right? Everybody's okay? So this graph of f of x is really the derivative of cap f, right? What does the derivative tell us about the function? Tells it where the function is increasing and decreasing, right? So we're decreasing from 0 to 1. We're increasing from 1 to 3. And then we're decreasing greater than 3. What's the other piece that I need to know about, though, before I can graph this? Also need to know about the concavity, whether the graph should be concave up or concave down. What tells me about concavity? Second derivative. So that's going to be the first derivative of little f, which is the same as the second derivative of capital F, right? So if I look here, we have the second derivative is 0 at the two extrema. Everybody's good there? From 0 to 2, the graph of little f is increasing. So the second derivative of cap f is positive. From 2 to 4, it's the graph of little f is decreasing. So the graph of cap f double prime is negative. And then after 4, the graph of little f is increasing. So the graph of cap f double prime is positive. Is everybody okay with how I've drawn the second derivative? So this is like concave up, concave down, concave up. Everybody's good? All right. So we decrease to 1, and we're concave up. Since we changed from decreasing to increasing at 1, we know that's a minimum. And we change at 3 from increasing to decreasing. And at 2, we have our inflection point where we're changing from concave up to concave down. You see how before 3, it's like a cup that's going to catch the water. And after 3, it's more like a mound where the water would run off. You guys see? At 3, the first derivative changes from positive to negative. So that's like our maximum. And then we're concave down until 4. And we're still negative after 4, or we're still decreasing after 4, but now we're changing to concave up. Try that one more time. So that would be like my graph of cap f, or the antiderivative. So I'm just going to use the graph of the original function as my first derivative and the graph of its derivative as my second derivative to figure out how to draw cap f using increasing and decreasing, concave up and down. Does that feel okay? Notice that the y coordinates did not really matter other than the starting spot, right? I have no idea where those maximums or minimums are going to be at, or the inflection points other than their x coordinates. I don't know where the y should be. So that's why it's a rough sketch instead of like the actual graph. I'm just guessing at a y. Doesn't matter. As long as your x's are in the right spot and your graph is increasing and decreasing and concave up and down in the right places, doesn't matter where the y values are, other than the starting one, which was given to you. It's okay? Feels very much like a first semester problem, right? We've done things similar to this in first semester. Okay. 2 last story problems and we're out of here. So it says a particle moves in a straight line and has acceleration given by a of t equals yada, yada, yada. Its initial velocity is -6. Its initial displacement is 9. Find its position function. So remember that if I take a position and I do its derivative, I get velocity. If I take the velocity and do the derivative, I get acceleration. Here we're asked to go from acceleration to velocity to position. What are we being asked to do here? Antiderivatives, right? Yeah, doing a second antiderivative. Perfect. So let's start by finding the general antiderivative for velocity. So I'll find the antiderivative of 6t. We'll write it this way, I guess. Plus, and the antiderivative of 4t. I'll make it general. What's c have to be? -6, right? So if I do s of t, the next antiderivative, the second antiderivative, what's c have to be? 9. So I'm going to have and we're done, right? No big deal there. Feels the same as the other ones. It's just we've packaged this as a physics problem instead of a just a arbitrary function. So you have to remember that the relationship between position, velocity, and acceleration, but like, whoop-de-dee-doo, not a big deal. I remember that. Here we say a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height? When does it hit the ground? What is that speed of 48 feet per second? Ball is thrown upward with a speed of 48 feet per second. What is that telling me? 1 second, guys. Tells me v of 0 is 48. From the edge of a cliff whose height is 432 feet above the ground, h of 0 is 432. Where do I start? Physics students. Acceleration is negative 9.8 constant, not negative 10. It hurts my heart when you do this in physics. Hurts my heart. So it's the same process as before now, right? And I'm out of time, so you guys can go. I just wanted to like stave past the setup. Next time, please do the related rates problems. Please be ready for your little homework quiz. We'll talk about both the related rates problems and the homework next time.